You have fallen into Event Horizon with John Michael Godier.
When you do what I do, you have to stay informed. Whether it's thinking about an Event Horizon interview, writing a hard science fiction novel, or writing a science video for my original channel, all of it requires being informed. And it's fun going through the news, scientific papers, and analysis to pull out stories that catch my eye to talk about. There are many such sources, but one of my favorites is The Economist, covering everything from world affairs to the latest in artificial intelligence with a dedicated section for that. The Economist also covers all the latest in science and technology news. That's why I'm happy that The Economist is sponsoring today's video. Their global reporting and analysis connects the dots between world events, technology, science, and the bigger ideas we discuss here on Event Horizon. They don't just report the news, they explain why it matters, breaking down complex topics in a way that sparks new questions and ideas. In fact, I was just reading an article that caught my attention. Scientists have now engineered mice to resemble miniature woolly mammoths, complete with thick fur and adaptations for the cold, leaving one to wonder if a resurrected mammoth would recoil in terror at the sight of a tiny fuzzy imposter scurrying underfoot. This experiment is a proof of concept for the eventual resurrection of the woolly mammoth, a creature extinct for thousands of years, but now on the verge of making a very confused comeback. But with this success, a bigger question emerges. Just what else can we bring back next? And once we do, then what happens? So if you're like me and love going beyond the headlines, The Economist is the source to read or listen to, with their narrated articles and podcasts. And as a listener of Event Horizon, you can receive 20% off your first year subscription. Just go to www.economist.com/eventhorizon to get started.
John is joined today by Dr. Daniel Brady Mills. Dr. Daniel Brady Mills is a DFG-funded postdoctoral researcher at Ludwig Maximilians Universität München, working in the ORSI Geomicrobiology Lab. He is also an affiliate member of the Penn State Extraterrestrial Intelligence Research Center. His research interests lie at the intersection of geobiology and astrobiology, focusing on the coevolution of life and Earth's environment, and the implications for the search for intelligent life elsewhere in the universe.
Daniel Brady Mills, welcome to the program.
Thanks for having me. It's great to be here.
Now, Daniel, there are people that make, within astrobiology, there are people that make all kinds of arguments that say, well, maybe the Great Silence is best explained by the idea that intelligent life is rare, and that to get to that point takes too many steps. And one of those steps is that maybe Earth is rare. Maybe the idea that our planet was hit by Theia and threw off a moon is the game changer for intelligent life. But I don't think that is the case. Rather, the conditions for this planet weren't quite there to produce us as a technological civilization up until recently. And it is towards the end of the life of the sun, towards it. But there are also things like orange dwarfs that would have much longer periods of habitability than the sun does. Your paper goes deeply into that, and the idea that maybe this planet hid intelligence, perhaps, the very first moment it could, and that before then, it wasn't really capable of producing something like us. Explain that.
Yeah, right. So the sorts of conditions that make the Earth hospitable to ourselves and other large animals, and also our technological civilization, in particular, oxygen levels in the atmosphere that are not only conducive to our metabolism and our respiration, but are also supportive of combustion. Fire did not always exist on Earth. Fire is a relatively recent phenomenon on the planet because you need oxygen. And you also need things to burn. And plants and wood have also not always been here. But you need this kind of atmosphere to support beings like ourselves physiologically, and also to support things like metallurgy or clearing land for agriculture, cooking, all these sorts of things that were essential to the origin of our civilization. And these oxygen levels, the oxygen levels required to permit beings like ourselves and technology, have only been present on Earth for not a very long time, geologically speaking. So, for over 90% of Earth's total existence, the atmosphere was not conducive to beings like ourselves and a technological civilization like the one that we make. So, for the vast majority of Earth's history, it just wasn't an option. And life couldn't have made that transition if it wanted to before the environmental conditions were right.
Now, my immediate question here that pops in my brain is that, okay, the octopus does not smelt metal, nor does it hammer the metal into an arrow point and fire it at its prey. So the oceans appear to be a delineating factor here between something that lives on land versus something that lives in the ocean. Do you think, and it's a two-part question, do you think that there are planets, water planets in this universe where they can be as intelligent as they want, but if you can't smelt metal, you're not going anywhere, and that means you live in an ocean? And the second part is, did life have to end up on land or end back up on land in order to reach technological capability? In other words, is water the showstopper? The giver of life is also the showstopper of life.
Yeah, these are great questions. I've thought of these too. I'll answer the second one first. So, of course, that's our particular trajectory. Our evolutionary history did, of course, involve our ancestors coming onto land and developing our technology on land in a way that was only possible on land. So, to the first question, on another planet where maybe that's not even an option, life is necessarily constrained to the marine realm, they would obviously not be able to follow the same kind of trajectory that humans did on Earth. And one way of interpreting that is that, yeah, that's a showstopper right there. They're not able to progress or develop, I shouldn't say progress, like develop the kinds of technology that we did in the same way. But I have heard conversations like this, like at SETI meetings, and people get creative and people wonder maybe they can use lenses underwater to concentrate sunlight and use that to do high temperature metalworking. I really don't know. It's an interesting question. But yeah, at least when we're thinking about beings that have followed the trajectory that we have taken, that would obviously not be an option on a water world. But again, it's a reasonable starting point to look at Earth and our own existence as like a starting point, and then imagining alternatives that could significantly deviate from our path, but maybe yield similar results. That takes some imagination, and I don't want to rule it out. Maybe these beings on ocean worlds can get creative, but we would take some level of imagination for us since we didn't take that path ourselves, and nothing else on Earth has clearly done that so far.
That's actually a creepy notion that I have never thought of before, using lenses underneath water. In other words, we know that nature can actually produce a lens, trilobite eyes, basically compound eyes that actually are lenses. And if you took the carapace of a dead trilobite and you were around a really bright star like an F-type star, if it's possible to maintain an ocean around such a thing, then you might be able to do something. But you also, I guess the obvious one would be volcanism. You've got volcanic heat down there. Maybe you can figure out how to smelt some kind of metal in an ocean. But fundamentally, the octopus has not done this.
Yeah, exactly.
The octopus is not the octopus is not producing an automobile yet. Do you think, though, that timelines are important here? Because if humans could only have appeared now, with our oxygen levels, could it simply be that we are the earliest in the game as far as technological intelligence? I don't want to demean the animals because some of them are very intelligent, but technological intelligence, that we can build a CD player or something like that. Is it that we are early and that this planet might produce other species over the remaining, 600 million years or so of ideal habitability for this planet? Could it be that other animals could arise and that there would be an explosion of intelligence on this world, which obviously has major implications for astrobiology? Is this planet moving to becoming smarter?
Yeah, I love that question. So first off, I'll say, like, when I talk about the oxygen levels now, I'm referring to the past 400 million years or so. So that's a very long time. But again, it represents a very small fraction of Earth's total history. And there's a couple of possibilities. My co-author, Adam Frank, was on a paper where they proposed something called the Silurian hypothesis. Not to be confused with the geologic interval, but it's a reference to a Doctor Who episode where there were a race of reptilian beings, I believe, called the Silurians that existed in Earth's past and then were somehow resurrected or they woke up. I don't know. I never saw the episode. But the idea that Adam was putting forth in his co-author, whose name escapes me, is that, it could be in their logic that maybe a couple 100 million years ago, let's say, there may have been a technological civilization, and that's not that long ago with respect to the totality of Earth's existence, but it's long enough ago that any kind of record of their existence, they went extinct presumably, would have been eroded away. There would be no, or whatever signals would remain may be indistinguishable from non-technological sources. That's their argument. So that's one way of looking at it. The alternative is that no, maybe that's still anachronistic. Maybe life on Earth still wasn't ready to make that transition, even though oxygen was sufficient. In that case, we may be the first. And like you alluded to, the kinds of conditions that support us and other animals and large terrestrial plant ecosystems, we might have another, like you said, 600 million years, maybe even more. It could be over 1 billion years. You had RJ Graham from Chicago on not too long ago, and he has a recent paper about this. So the Earth may have a relatively long history or time in front of it that can provide additional opportunities for technological life to evolve. And I used to rule out the possibility that even given this sufficient time scale, it'd be unlikely for anything else like us to emerge. This has also been referred to as like the planet of the apes hypothesis. Like if we were to go extinct or go out of the way, our close relatives would take the position that we're now in. It doesn't have to be other primates. It could be talking about 600 million years. Primates are only, I don't know, 60 million years old or so. In 100, 200 million years, I think it's hard to imagine what kind of animals are going to be present on the Earth. And given, especially if we're out of the way, if we don't have descendants on the Earth at that time, whether we've gone extinct or we've left the Earth, who knows? But animal life literally is still able to evolve on the planet. Yeah, I think, yeah, and it doesn't even have to be a primate. It doesn't even have to be a mammal. Again, who knows what's going to be around in 200 million years? And I like this idea that, yeah, there could be other opportunities for the Earth to yield an intelligent civilization while it's still able to.
I like the idea from the Silurian hypothesis, in order building upon it anyway, is that maybe the solution to the Fermi paradox is that all alien civilizations, all evidence of them, gets subducted into their planet. And that brings in the idea that maybe we need plate tectonics in order to have intelligent life.
Yeah, of course.
And we don't see plate tectonics on terrestrial worlds in this, this solar system, except Earth. What is your view of rare Earth? In other words, let's start with the planet itself. Before we get to biology, let's start with the planet itself. People make the argument that this planet is rare. I counter that argument with this planet is one of countless untold planets sitting in the habitable zones of stars. There's no reason why you wouldn't be in your habitable zone. It's not off limits to planets for any star. Well, any main sequence star anyway, from type F and below. But the thing is that there's no reason to suspect inherently that Earth's place in the solar system is rare. People make arguments. What's your view on the rare Earth hypotheses? And also, biology finds a way, life finds a way, the famous movie quote. The resiliency of life may overcome this. What are your views on that?
So the rare Earth hypothesis, I need to give Don Brownlee and Peter Ward a lot of credit. These are the authors of the book Rare Earth. This was the book that actually got me interested in this research. I read that book just when I was entering my bachelor's degree. And I actually was an anthropology major at the time, or a declared anthropology major. And I read this book and I thought it was the most interesting book I've ever read. And I couldn't believe that scientists were actually working on these things. They covered a lot of things in that book that I had never heard of in my high school education. So that book was really inspiring. And I've reached out to Peter Ward to thank him for this. And I was absolutely convinced of the rare earth hypothesis. Like it was very compelling to me when I first read it. I'm like 18 at this time. And I kind of carried that perspective with me throughout my bachelor's degree and my PhD. And it's only very recently that I've started to come around and think differently about it. So I just want to say I sympathize with the rare earth hypothesis, and I know what it's like to be an advocate myself, my firsthand perspective. But yeah, I would say we simply don't know. We simply don't know how rare or how unlikely Earth's its distance from the sun and its size, its composition, also its that it has the moon that it has, that in the outer solar system there are large gas giants that can potentially protect us from large impacts and these sorts of things. I don't think we know yet how representative the Earth is amongst other habitable planets in, their respective habitable zones and so on. We simply don't know, but it does raise all these interesting questions, which drives a lot of my research, is what does a planet need in order to make this transition? And that transition, I mean, the rare earth hypothesis essentially argues that the origin of life isn't so much a problem. There might be a lot of habitable, inhabited worlds out there, but they're exclusively microbial. The life forms on these planets never evolve into the sorts of large macroscopic forms we see on Earth and plants and animals and so on. And that transition in Earth's history is relatively recent. It happened a little more than 500 million years ago, where the biosphere kind of blossomed into the state it's in now, with large animals and plants comprising terrestrial marine ecosystems. But that transition on Earth is so poorly known, and that's where a lot of my work as a PhD student was focused on. And a lot of the people who study that are geologists and geochemists, paleontologists, who aren't necessarily considering the role of the moon in all this or the role of Jupiter in all this. We're more interested in it from an internal perspective, like the Earth, like Earth's biogeochemical cycles and supercontinental cycles and the climate, and how did this all come together to facilitate this transition. And this period, this is called the Neoproterozoic era. It's between 1 billion years and a little more than 500 million years ago. It was a very tumultuous and revolutionary interval of Earth's history, and it's poorly understood. We don't really understand. It witnessed all these crazy events, like snowball Earth events, at least 2, where you have glaciers at the equator, a supercontinent broke up. It looks like there were really enigmatic oscillations in the carbon cycle, maybe nutrient cycles were changing, and life was flourishing, specifically eukaryote life, the kind of life that we represent, cells with nuclei and mitochondria. They were proliferating at this time, including the earliest macroscopic multicellular animal forms in the fossil record. So this was incredibly dramatic transition. And that's the key difference between, in the rare earth context, exclusively microbial worlds and worlds like our own that are able to make this transition to a high oxygen, high biodiverse Earth surface. Again, I would say we simply don't really understand this transition well enough, but I don't see any evidence that would lead me to say that it was definitively unlikely or improbable and Earth just got lucky. I see no reason why other inhabited planets, given sufficient time, would go through the same transition. Of course, these planets have to be physically capable of making these changes, and I agree that plate tectonics would be important. These planetary bodies have to be arranged in such a way that they have to be able to accommodate a rise of oxygen like the one that we saw around this time in Earth's history. But we're beginning to constrain these things. And right now, I would say there's no definitive evidence that was an incredibly unlikely transition and that we should not expect other habitable planets to go through it themselves.
We can call it for our purposes here today, but I don't suggest going any further. Don't put this in a paper. The lazy Earth hypothesis, in that Earth may have it may have taken it a little too long. The leap between prokaryotic to eukaryotic life took a long, long time. Do you envision that it's possible for a planet to leapfrog all of that and actually become habitable on a much shorter time scale? Not habitable, but achieve intelligent life on a much shorter time scale than Earth did? Could this have happened faster?
Yeah, absolutely. And the first time I heard that written in the literature is from a paper I only found relatively recently while writing this hard steps paper. It was actually a book chapter, I believe, from 1985, written by Andy Knoll, who's a geobiologist at Harvard. And he was actually responding to Brandon Carter's hard steps argument. And this was really valuable because not many people in my field in geobiology have really responded to these sorts of arguments. And if anyone's going to respond, you would want Andy Knoll to respond. He's very reasonable, incredibly thoughtful, incredibly knowledgeable. And I really liked his response to the hard steps problem. And he raises this possibility that you just raised. And actually this possibility was also raised in a really short Nature article. It was more like a news article in the early 80s, also responding to Brandon Carter. And both this paper and Andy Knoll raised this possibility that, yeah, maybe life on Earth actually took longer than other planets. Other planets have made the comparable, analogous transitions in habitability on much shorter timescales. And that Earth just represents, like you said, Earth is relatively lazy compared to these other planets. And it goes to show how little we know, because we're all extrapolating from one example. We don't know if the tempo of Earth's environmental and biological change is characteristic, like what happens on most habitable planets, or maybe it's much slower than it normally takes. If it's faster, maybe that's essentially what Carter argued, that it happened uncharacteristically fast. We were able to evolve before the Earth lost its capacity to host life. But yeah, we don't know. And I can imagine if you had an Earth-like planet, like a rocky planet in the habitable zone, capable of plate tectonics, given slightly different starting conditions, maybe it could have gone through these sorts of transitions on much shorter timescales. That's completely reasonable. And Andy Knoll raised that point in 85, and I think it's a good one.
Do you think, and this raises a certain specter, perhaps even lazier than Earth, or perhaps not, ice shell moons that have water oceans underneath shells of ice, as places like Europa and Enceladus do? If we are discussing the idea of leaving the ocean or smelting metal in the ocean, do you think that there is an inherent disadvantage towards ice shell moons as ostensibly being able to harbor life, but can't produce civilizations, and that the solution to the Fermi paradox is simply that most life is locked under ice?
Yeah, I think that's super interesting. Yeah, I think it would be a challenge. Again, that would represent they would not be able to take the path that our lineage has taken, right? That wouldn't be an option to them. Then it raises the question, what possibilities would be available to them if maybe they are able to have complex societies, but in a way that we have not observed on Earth yet. Yeah, I don't know. Yeah, I think it would be a barrier. But again, it's one of those things, imagining life as we don't know it, or civilizations as we don't know them. Yeah, they could get creative. I don't know. But they might have remarkably sophisticated societies, but they don't leave the shell of their ice world. That could be it.
Or maybe they do. Freeman Dyson long ago put out there the idea of Dyson's sunflowers, where you have life and it somehow makes it up through the cracks, and it somehow is able to concentrate sunlight and somehow sever itself from its ice shell moon and go and inhabit asteroids. Is that a step too far? In other words, do you think that there's a fundamental limit that intelligence in biology reaches, then it cannot go any further, and that there are no Kardashev type 2 or 3 civilizations? There are only at best type 1.
Yeah, the first thought I had, if it's leaving the ice, if this is an organism, it makes me think of does it have any kind of atmospheric protection? I don't know enough about these worlds to know if it could even leave the ice and be viable. But then it made me think that the way we explore space, if a technological civilization did emerge on one of these sorts of icy worlds, they would similarly, want to know what's on the other side of this ice at the top of their world. So maybe they would send probes out there to do exactly what you just described or Freeman Dyson described. But I don't know. I've not heard of that idea before, but it's interesting.
It's just a dalliance in the idea that we don't completely know what life can do. We only know what Earth life does. And we can sort of think maybe life could do this or that. Thoughts on that? Do you think that perhaps our ideas of carbon chemistry and oxygen use might be a little bit misguided, and that chemically somewhere within the the incomplete realm of chemistry, that something like silicon life or something like life based on another solvent other than water might be out there and might have different rules as far as reaching intelligence than Earth does.
Yeah, these are good questions. These sorts of questions come up a lot at these astrobiology meetings and SETI meetings that I've been to. It's always hard to tell. Again, we have an N of one, and it's hard to discern what is necessary about life in our biochemistry and what's contingent. But given that, I do think there are constraints, and these constraints transcend biology. It's chemistry and physics, and not everything we can imagine, I think, is realizable by the universe as we know it. So I think there are limits, but it's really hard to identify what they are exactly. I think with respect to like water as the solvent is life, carbon, there are a lot of properties of water and carbon that make them particularly good for making life. I don't think that's completely contingent. And same with oxygen. I think, well, if we're talking about like a water-based, carbon-based life, when it comes to metabolism, oxygen, I think, really is the best candidate. And that has to do with the energetics of oxygen and aerobic metabolism. That I think oxygen, that's not contingent. I think it's very reasonable to think that other animal-like beings or human-like beings in other worlds would similarly respire oxygen for the same exact reasons that we do on Earth. But at the same time, I do want to be open-minded, and I know nature is more creative than we can imagine. So it's full of surprises, and I bet there are worlds out there that would challenge a lot of what we think is true about life in the universe, but it's life as we can't imagine it. I can't imagine it. So I usually in these approaches, I take a more operational approach and say, we're just starting to search, more or less. It makes sense to look for what we know, what we're familiar with. And I think there's a good amount of evidence to suggest that our biochemistry and our metabolism isn't completely contingent. And I would say this has to do more with chemistry, which would be the same on other planets. So I think there are constraints, but it's a good exercise to identify those constraints.
That's one that I wonder about, is the production of oxygen and hitting on photosynthesis. It seems to me that there isn't any real barrier, at least that we know of right now. There isn't any real barrier to that the great oxygenation event having happened much earlier on Earth. And that's the lazy Earth hypothesis again, that maybe the production of oxygen might have happened earlier on this world than it did, and by chance it just simply did not. However, the oxygen levels of this planet, you go into this in your paper, the oxygen levels of this planet have varied, and we are in a sort of different period than there used to be. There have been times where it had more oxygen and less oxygen. And you mentioned before about fire, that at times it was not possible, but at times it might have been even more possible. Yet a dinosaur in the Cretaceous or something like that, whatever, did not master fire. So how do you rectify intelligence versus the availability of oxygen? And can there be too much oxygen? In other words, can you have a planet that just resets itself because its plants are making too much oxygen for a civilization to develop because everything burns down before it has a chance to develop?
Right. So this is concerning like the mechanisms that control the amount of oxygen in the atmosphere, which is a very active area of research. And there are feedbacks, it appears, in Earth's biogeochemical cycling that would prevent oxygen levels that are too high. And it's essentially that as oxygen gets even higher, like you alluded to, like, yeah, maybe in the Carboniferous or so, maybe oxygen was higher than it is now. That makes forest fires much more likely. So if lightning strikes in a forest and it starts a fire, that higher oxygen will serve as fuel, and these forest fires would be more devastating, right? But then what would happen is it kills all these plants, right, as they burn, and then oxygen production would be shut down because they're dead, right? So that there'd be some kind of stabilizing feedback to prevent oxygen levels from getting too high. But this is the difficult question, how exactly oxygen levels on Earth, or even the past, let's just say the past 500 million years, how they've been regulated. That a lot of people are working on that. But it does appear that there are stabilizing feedbacks to prevent oxygen from becoming too high. But yeah, if a technological civilization was trying to start itself with oxygen levels that are higher than today's, yeah, maybe that would have been a barrier. They would have had to deal with fire in a way that our ancestors did not. But I don't know if it would have been a complete barrier to their existence at all. Or maybe they still would have been able to make a civilization, but they would just have to protect themselves from these sorts of devastating forest fires that would have been raging through the earth. But yeah, I don't think that would have been a problem too high oxygen. Well, given the mechanisms that control oxygen in the atmosphere, that would ultimately, on geologic timescales, bring it back down. But yeah, that's a good question. I haven't thought of that.
Another thing I thought about is, well, if you have a higher fire rate, more oxygen, more fires, wouldn't that push evolution to make fireproof plants and fire resistant?
Yeah.
Much more so than, they don't, our trees don't have to have it here, even though actually some of them have actually evolved a certain resistance to fire, and that very rapid wildfires move through, and some of them survive it. They're designed for fast fires. But fundamentally, in a worse environment, this with higher oxygen, maybe the plants just evolve anti-fire, so that they don't burn and they get past it that way.
Yeah, why not? Yeah, no, I like that idea. No, like if oxygen was not able to go down to a lower level, it had to stay at these levels for whatever reason, imagine on another planet. Yeah, then maybe the plant analogs in that world would, yeah, have to necessarily evolve ways to be more fire resistant. Yeah, I don't see why not.
Do you think, though, that chemically speaking, anyway, that when you add more oxygen to an atmosphere, you change the chemistry such that maybe there is some sort of ultimate equilibrium? In other words, if you've got hydrogen seeping up out of the planet, which Earth does, white hydrogen from geology, serpentization, things like that, eventually you get to the point where you can't have more oxygen than a certain level because it all eventually turns into water and combusts.
Right. We did talk about this a little bit in the paper, imagining other inhabited worlds that, given their like internal chemistry and structure, maybe would not permit either the permanent oxygenation of their atmosphere, like oxygen would not be able to become like a stable feature above trace levels, or maybe these planets would permit like the oxygenation of their atmospheres, but not beyond a certain level. That's a good point. Like after the what's called the Great Oxygenation Event, like maybe 2.5 billion years ago, let's say, oxygen became a stable feature of the atmosphere, but it stabilized. It looked like, this is a huge area of debate, but it stabilized maybe between 1 and 10% of modern levels, maybe even below 1%. This is a huge debate. But the point is, it stayed at non-modern levels for a long time until it reached modern levels, maybe only over 400 million years ago. So, and this is a huge area of research. Like, how did the Earth stabilize at those low, non-zero, but non-modern oxygen levels for such an extensive period of Earth's history? That's a huge area of research. Yeah, I think it's easy to imagine other worlds that maybe that's it. That's as far as they go, and they can't get beyond that. At the same time, I could also imagine other worlds that are able to accommodate that transition and then reach levels comparable, oxygen levels comparable to what we have on Earth now, in a shorter time than it took Earth to make that transition.
Now, to go the opposite of rare earth, let me ask you this question. Better than Earth. Can you envision an exoplanet that is better suited for life and ultimately a civilization than Earth is? And I can give you one example. That type G sun is not ideal. It's much shorter lived than an orange dwarf, a type K. So that's one avenue for better than Earth. Can you think of others?
That's a really good question. I've actually never thought of that. So what would be better? It's hard to say. Like I alluded to, maybe there are Earth-like planets that can go through these sorts of major environmental transitions, like the oxygenation of the atmosphere, on shorter timescales. That would be better in the sense that life like we have on the modern Earth could be achieved more rapidly, if that means better. But even then, we propose that in the paper, but we would have to do some follow-up work to figure out what exactly that planet how we would need to differ from Earth in order to accommodate such rapid changes. I don't know what those are yet. But yeah, I don't know. This is an interesting question because even there are other ways of assessing better. Like if these planets can somehow be more productive, like autotrophic life that builds itself from gaseous CO2, like plants essentially, photoautotrophs, but also like chemolithoautotrophs that do this with chemical energy. Like if you could have a planet that's somehow more productive, much more productive than the modern Earth, then there'd be a lot more energy flowing through these ecosystems. And maybe that would permit levels of ecosystem complexity that the Earth has not realized. I don't know. But I have to think about this. This is a good question.
Things that Earth has not really done. The idea that we have two gas breathers, two different classes of gas breathers on this world, and one is oxygen, the other is carbon dioxide. What we don't really have, and they're in, of course, in an equilibrium where we're breathing oxygen and giving out carbon dioxide, and the plants are taking in carbon dioxide and releasing oxygen. Can you think of a hybrid where a hypothetical species could make use of both chemical paths to producing energy?
Well, we do have microbial eukaryotes, for example. So these are not bacteria. They're eukaryotic cells. Our own cells are eukaryotic. But you have examples of what's called mixotrophies. They're mixotrophs. So they can photosynthesize. They have chloroplasts and they're able to perform oxygen releasing photosynthesis, but they're also able to eat other cells for nutrition and get their carbon that way from organic matter, living organic matter, as opposed to CO2. So they're actually able to perform both. And there are even microbial eukaryotes or protists like this, where you put them in the dark and they'll eat their chloroplasts and they'll live, like as a non-photosynthetic, microbial eukaryote eating other cells for nutrition. But if you leave them in the light, they'll maintain their photosynthetic capabilities. So that does exist on Earth, mixotrophy. I don't know if that's exactly what you were referring to, but something like that does exist.
Yes, that's what I was getting at. And what of methane? In other words, you can burn methane. It's natural gas, meaning that it's an energy source. Does anything on Earth actually, other than producing methane, which also can very much be produced by geology, but does anything use methane as an energy source?
Yeah, absolutely. So they're called methanotrophs, which just means they're methane eaters. For example, they can breathe oxygen the way we breathe oxygen, but in their metabolism, they're pulling electrons from methane. Methane is their food, or the electron donor, as they say. Yeah, and they eat methane essentially. So yeah, methanotrophs are a type of organism on this planet.
Yeah, and that gets into just what elements, reactive elements, that things can eat. And this planet has iron eaters.
Exactly.
Bacteria that can eat iron and use the oxidation process of iron to power themselves. But how does that contrast with oxygen? In other words, yes, you can eat iron and you can eat methane, but it isn't going to give you the crazy reactivity of oxygen. Is that ultimately a potential showstopper for intelligent life? Without oxygen, yeah, you can have life, you can have all these things. Earth didn't really have much oxygen originally until photosynthesis and the great oxygenation event. But is it possible that the reactivity of oxygen is the solution here, in that nothing quite compares to it?
Yeah, that's right. So there are a lot of different ways to make a living on Earth, and it's really like the bacteria and the archaea that really represent most of Earth's metabolic diversity. So all the different ways that life can conserve energy from the environment. Eukaryotes like us are actually pretty boring. We pretty much only, ferment, breathe oxygen, or photosynthesize. And some can breathe nitrate, for example. But yeah, like all things being equal, like if you look at like all life needs like an electron source, and then for things that respire, they need a place for those electrons to go, the electron acceptor, and that's what oxygen serves for us. And if you look at these different pairings of electron donors and electron acceptors, they all are associated with different energy releases. They all release different amounts of energy that can be conserved, through ATP formation to perform biological processes in the cell. And none of them yield more energy for this kind of biological work than oxygen. And, there are other pairings you can make, that like chemically would yield more oxygen or yield more energy, but they're not compatible with our biochemistry. Like I think fluorine could be another, it would yield even more energy than oxygen using the same substrate or electron donor. But fluorine isn't compatible with our biochemistry. It's very destructive. It's that's a limit. So again, given the constraints of the periodic table, oxygen really does seem to be the most energy yielding electron acceptor given Earth's biochemistry and the sorts of chemical energy that's available to life on the planet. And that's why people think oxygen, it's not contingent. They're very specific bioenergetic or metabolic reasons why we breathe oxygen. And we would predict beings like ourselves to also respire oxygen on their respective worlds.
Yes, and it has to be said, something like fluorine is a lot rarer than oxygen. There are not so many ways to produce a lot of fluorine, an abundance of it. And oxygen, it's everywhere. We see it in nebulas, abiotic oxygen. It just stars produce it. So it is a much more common item, and you can make that argument with solvents too, because water's everywhere, comets, and there's all kinds of sources for water. Not so much for the other potential solvents that could host the chemistry and not destroy it of life. But my question for you here is in regards to, scarcity. The chemicals of nature must play a part in life and whether life can arise. And one thing that people often point out is phosphorus, that there are observations, and they're not well constrained, but there are observations that phosphorus is spotty in the Milky Way and that there are phosphorus poor areas, and that's led to a different variation of the phosphorus problem. Unfortunately, it shares a name with another problem with phosphorus. But do you think that scarcity of certain elements is going to play into the Fermi paradox ultimately for the Milky Way, and that unless you got the right mix of chemicals, you're not getting anywhere?
Yeah, I think so. And I think this would represent a fundamental constraint because even it looks like, the early Earth wasn't as productive as the modern Earth. It's not just oxygen availability. There wasn't as much like what we say carbon fixation, like autotrophs building their bodies, their cells out of CO2, this kind of primary productivity that then fuels like heterotrophic ecology and so on. It looks like primary productivity was much lower on the early Earth, and that phosphorus availability actually played a big role in keeping productivity low, and that actually phosphorus levels in the ocean needed to increase in order for ecosystems on Earth to become more productive and to become as productive as they are now. So I think even looking at Earth's history, we can see how the limited availability of different nutrients has actually throttled or constrained, the sorts of ecosystems that the Earth was able to host. And that's a huge area of research in geobiology, people who are trying to reconstruct the evolutionary history of Earth's surface environment and Earth's ecosystems over time, and trying to understand the controls on phosphorus availability and reconstructing, ancient phosphorus levels in the oceans over Earth's history and relating that to productivity. That's a huge area of research. But I think even though we have a lot to learn, it's very clear that these sorts of nutrients are incredibly important in determining the sorts of life and the sorts of ecosystems that the Earth can host.
Cross-disciplinary importance here. Now, within SETI, it's no secret that for most of SETI, even today, it's a bunch of astronomers. It's a bunch of astronomers and,
yes.
and geobiologists are not really well presented. How do you bridge the gap to, allow a diversity of thought on these questions? How do you bridge the gap with SETI as a geobiologist to get a broader perspective and how we even think about what we look for regarding life?
Yeah, so this is a really interesting question. I will say this, though, in the SETI meetings that I've gone to, I've been really impressed. I would say this, they're mostly, astronomers, but they're so, and I don't know if this is about astronomers in general or the sorts of astronomers who go to SETI meetings, but they're so open-minded. Like and they want to listen. Like they ask a lot of questions and they care about the answers, and they're really eager for this kind of cross-disciplinary interaction. And I really like that. I found that to be really welcoming. And I actually think it's a really safe community for geobiologists and biologists and paleontologists and so on to join, because there's a lot of freedom. There's a lot of, exploring new ideas and a lot of intellectual freedom, I would say. And yeah, I think a lot of geobiologists are becoming members, not only of SETI per se, but also the search for exoplanetary biosignatures. I think that entire endeavor has recruited a lot of people from geobiology, people who like to model or reconstruct the composition of Earth's early atmosphere and how it's changed over time, because it raises questions like, okay, well, how would we recognize, it's one thing to try to recognize an exoplanet that looks like Earth now, but what about exoplanets that look like the way Earth did 1 billion years ago or 2 billion years ago? Because the Earth has looked very different. Its atmospheric spectrum is completely different at these different times. So they're taking in, the field of exoplanet research is taking in a lot of people from the Earth history community, which I think is great. But at the same time, I think SETI would benefit from more geobiologists, evolutionary biologists in particular. But I will say this, at the SETI meetings I've been to, like one organized by Jason Wright, the PSETI meeting, he's making a really clear effort to bring in these other researchers, and not only from the sciences, but also, from the social sciences. Even artists. I've met artists at these meetings, and Jason, for example, is really keen on bringing in as many experts as he can to join this conversation. So I think that's great. I think SETI is very welcoming. I think what it would take is for people from these other disciplines to kind of join in on the conversation.
Yes, it actually, I've come across the same thing, is that it's open because, the astronomers, they know. They're like, how do I think like an alien? And it's even worse, how do I think like an alien bacteria? Or is it even an analog to bacteria? So there's all these open questions. It's just that you have to get everybody involved. And I think that's really what they're pushing towards, is to try to get other disciplines into the mix to think of the things that the astronomers didn't, because it's just simply not their specialization. What brings you to astrobiology? What happened with you that said, I really am fascinated with the possibility of alien life, or what life can do?
Well, I mean, I guess I was always interested in the prospect for alien life, like as a kid watching science fiction and so on. And like I said, when I read Rare Earth when I was about 18 or so, that's when I realized that there were actually scientists who are working on these problems, which was news to me. And as an undergraduate student, I actually minored in astrobiology at Penn State. Penn State was a NASA astrobiology research center at that time, and there was actually a lot of support for undergrads like myself at the time. Like, they sent me to an astrobiology science conference meeting in 2010. They funded a field trip to this really low pH acidic river in Spain, the Rio Tinto, sometimes used as a Martian analog. So I was really involved in the astrobiology research at Penn State while I was there, and working in Jen McElady's geomicrobiology lab, and she's the second author on this paper. But then when I went to do my doctorate work, I really focused in on Earth's past and Earth's evolution, which I was happy to do because that's my primary research interest. And the people I was working with weren't so interested in astrobiology for their own reasons, and that was okay with me because I was interested in this other stuff. But I did feel kind of out of the loop, and it was always in the back of my mind. Like, even the papers I wrote as a doctorate student, they did have a lot of implications. For example, like for the rare earth hypothesis, or even the hard steps model. But I wasn't explicitly writing about these ideas. They weren't in the discussion sections of these papers, but I was always thinking in the back of my mind, and in reading astrobiology papers. But then, and I continued this trend as a postdoctoral researcher. But then Jen, my old advisor at Penn State, got involved in the PSETI Center at Penn State. And she invited me in as an affiliate member to participate in a series of discussions we were having back like in 2020, 2021 or so on Zoom about this hard steps model. So she brought me in to see what I had to say about it. And I jumped on the opportunity because like I was kind of waiting for, let's say, like permission to work on these things, as part of my day job instead of just thinking about it at the end of the day. And so I was really excited to join these conversations. So that's really where this paper originated, through a series of conversations we had on Zoom, a few years ago. And then we had enough conversations and enough ideas that we were able to write a paper about it. And since then, I'd like to get more involved in astrobiology research. And I joined a couple of like scientific analysis groups at NASA looking at technosignatures. And so I'm excited. Now I feel like I'm kind of coming full circle back to my roots where I'm now able to actually do astrobiology research as my day job. And, that's really exciting.
What's going to be fun is that we have it within our capabilities, technological capabilities today, to either find a microbe that is, a separate abiogenesis on inside an ice shell moon, Europa, something like that. Or we could see a biosignature of an exoplanet, some weird equilibrium of gases, too much oxygen, these say a profile of gases that is best explained by a biosphere of life or the vegetative red edge or whatever you see. Or you see an alien civilization, a technological radio signal. Regardless, this all collapses in one day if you find a good, unambiguous candidate for life outside the Earth, and that this all becomes academic. All the arguing about rare earth and all that just disappears in a day. Do you anticipate that's going to happen within our lifetime?
Oh, I would love that. I mean, I've been dreaming about that, I think, most of my life. Would I want to be realistic to check my optimism. I am optimistic. I think in my lifetime, I do think we'll find a good biosignature candidate in an exoplanetary atmosphere, hopefully many exoplanetary atmospheres, because as you said, we have the technology and it's only going to get better in the near future. I think that's the most likely. I mean, I don't know what kind of unambiguous event you were referring to. I mean, of course, if that happened, it would throw all of this out the window. That would be amazing. I have no idea if it's going to happen. Yeah, so usually when I think about where is this going to go over the course of my lifetime, I'm like, I'd be pretty happy if by the end of my life, we have convincing biosignatures, like atmospheric biosignatures and exoplanets. But, I would love to be surprised and have something more unambiguous or interface show up.
Yeah, well, unambiguous in the sense that a radio signal that's clearly technological, that's pulsing out prime numbers or sending data, something like that. Because that's really the big problem with SETI is ambiguity. We have candidate signals, but for example, the WOW signal, we didn't really think of a way that could be natural up until recently, that some circumstance can produce a narrowband signal like that would look like that. So it was just an open question that everybody argued about for 35 years, something like that. And that's what I mean by ambiguity, is that it's always going to get called into question. If you say, hey, I see high oxygen levels in this exoplanet, and my hypothesis is that the only thing that can explain that is photosynthesis, you're going to have a bunch of other scientists that say not so fast. And it's ultimately becomes an exercise in ambiguity, and that's really what I meant, because things always get questioned, but if you saw something like a very obvious civilization building a Dyson sphere or whatever, then it goes beyond a threshold and you're like, yeah, that's what that has to be. But we've never seen anything like that. We just see the great silence. Daniel, thank you for joining us today. And I look forward to further papers. What are you working on next?
Oh, that's a very good question. Well, right now I'm working on more earthbound things, trying to reconstruct ecosystem change in the aftermath of snowball Earth in the Neoproterozoic. the impact that that had on eukaryote ecosystems. So for now, my work is still more earthbound, but I'm about to take a new stage in my career, a new step. And I hope to be more involved in testing the alternative to the hard steps model that we propose, and trying to work more full time on that.
Yeah, I hope you'll come back at some point, because that's something we could definitely discuss, is snowball Earth and how weird and different Earth would have looked when it was mostly frozen over, and how did life make it through that period. So I hope you come back.
I would love to. This was a lot of fun.